last lecture. So in the last lecture we discussed the definition of subbases. So X is the given set and a subbasis S uh, for a topology on X is, so S is the collection of subsets of X, right, whose union is X. So that is the definition we discussed in the last lecture. So on whatever set X, if I can find a collection of subsets of X whose union is X, then that family is known as subbasis for that set X, and every subbasis gives us a basis on that set X. So basis means basically we are discussing the topological basis, right? So every subbasis, whatever family we have S, we can take we will take all possible finite intersection of elements of this family S. So that is basis. So we check that this satisfy properties of basis on the set X, on the given set X, and since it is a basis, it generates a topology. And we discuss one example which is over the set of natural numbers. We have considered this subbasis, and we have verified that the topology generated by this subbasis is nothing but the cofinite topology on N. So this is what we discussed in the last lecture. So today I want to discuss product topology. So like if I have two vector space V and W, I can discuss V cross W, which is again a vector space, right? So same way, if I have two topological spaces X and Y, so tau X is a topology on X, tau Y is topology on Y, then using tau X and tau Y, I can define a topology on X cross Y. So that is product topology. So let us define that. So let X and Y be topological spaces. So what does we mean by this? X and Y are topological bases. That means tau X is a topology on X and tau Y is a topology on Y. So this is not part of definition. This is just meaning of the first sentence, that X and Y are topological spaces. So if I have two topological spaces, then the product of these two is known as product topology on the product space X cross Y. So product set is the topology having basis the collection B of all subsets of the form U cross V, where U is element of tau X and V is element of tau Y. Alright, so what is product topology? First of all, I know what is tau X is topology on X, tau Y is topology on Y. So now product topology is a topology on x cross y. So x cross y is a set on which we can define a topology. So for that, uh, if I want to define a topology, then what I will do, I will take the subsets. So in other words, I'm considering the family B, which is U cross V, where U is in tau x and V is in tau y. Right. So we want to show that this is a basis on x cross y. So let us uh, first define proposition. So B defined to be U cross V such that U is in tau x, V is in tau y is a basis for the set x cross y. So what we need to check here, what are the properties of basis? So for example, first property what we need to check, can anyone help me?
Sir, we will take a element from B. Sorry, X cross Y,
Oh yes, so let us
and
start
then
with some element of x cross y, and what we need to show,
that it belong to some basis element of B.
there is b element of b. So uh, right, so you are right. So what are the elements of b? They are of the form u cross v, right? So basically we have to find u cross v
But sir,
in,
hello,
yes,
सर X cross Y को पहले टोपोलॉजी प्रूव नहीं करेंगे?
x cross y एक सेट है, उसके ऊपर हमें एक टोपोलॉजी फाइंड करनी है. We need to find a topology. So what is a topology? Topology is a collection of subsets of x. If I need a topology on x, I have to find a, just a minute. Yeah, so my screen is visible.
Yes, sir.
Okay, so as I have written, tau is a
Yes,
subset
sir.
of our set of x, right? So this means tau is a topology on x. Now I want to find the topology. So I have two topologies, topology on x, topology on y. Now I want to find the topology, new topology, tau x cross y, which is a subset of power set of x cross y. So this topology, I am saying this is, I will get a topology which is generated by the basis, right? If I have a basis on x cross y, I can always get a topology by taking all the unions of the elements of the basis, right?
सर सर बेसिस correspond to X सेट थोड़ी होता है, बेसिस तो corresponding to टोपोलॉजी होता है ना, if I am not wrong. Basis is corresponding to
So
topology, is not corresponding to set X.
see, when we defined the basis, we did not define the topology, We just said basis is a collection of subsets of X which satisfies two properties, right? And the basis will gives us a topology corresponding to that basis. So what is the topology? Topology is the all unions of the basis elements. So that we define as tau b. So every b gives us a topology corresponding to that basis. So is it clear now?
Yes, sir. Yes.
Right? So every basis is what? Basis is a subset of power set of X which satisfies that two axioms of the basis. And then once we get a basis, then we take tau b, which is the union b alpha, where b alpha belongs to b. So now what I am saying here is that I know these two topologies, tau x and tau y, that is given. That is given two topologies. Tau x is topology on x, tau y is topology on y. Now I want a topology on x cross y. So to get that
So when
topology,
we are talking about the basis, then no particular topologies means that time there is not a particular topology defined on that X. We are
yes,
just
you are right.
simply saying that a basis for a topology on X.
Yes,
And for some topology on X, it will be like this.
yes, you are right.
Okay, and then after we have got that basis, then we will construct the topology. Means then we have found that topology on X
That is exactly
with
tau b.
respect to that basis.
Yes,
Tau b. Yes, yes. Okay, okay.
Yes, yes. Now got it clear. Thank you.
right. So yeah, that thing is clear. But now I am explaining how I am defining the product topology here. So I'm explaining now the definition of product topology. So product topology, I have two topologies. First is a topology on X, that is tau x. Second topology is on Y. Now I need third topology, which I will call product topology. So for product topology, we can use this type of notation if we want. So what is this? That is a question. So that is defined by this topology is defined here in this definition. So what is this topology? This topology is tau b. And what is this b? That b is exactly this set. Alright. Every b gives tau b. So that b we have defined here, which is basis for the product topology. So I have defined b. So is it clear? This b is a subset of power set of x cross y.
Yes, sir.
It is clear, right? Because u belongs to tau x. U belongs to tau x means u is a subset of x. Similarly, v belongs to tau y. That means v is a subset of y. And u is a subset of x, v is a subset of y. Then u cross v is a subset of x cross y. So this is a family of subsets of x cross y. Now we need to check that this is a basis. So that is what we were discussing. So first to discuss this first property, for every element of the set we have to find a basis element such that xy belongs to the basis element. So that is the first property we need to show. So what is the justification here? Justification means basically proof of this. why this is true. So what we will use, only thing we know in this definition is we have these two topologies, and we know u belongs to tau x and v belongs to tau y, right? So that is the only two things we know. So that we will use here. So since xy belongs to x cross y, x is in x and y is in y. So let us therefore what we will get is we will get there exists a basis element b in bx, so that x belongs to b, right? Because x is a topological space, so it has a basis. Similarly, y is in uh, so let me denote so bx and by. So let us take b small x. So y belongs to b small y.
Sir, the notation is not clear that we write written above in the so
So what is not clear?
means we are saying that there exists an element from basis set
Yes.
belonging to B such that जो अल्फा एलिमेंट है वो उसमें आ जाए. Okay, okay. Sorry, sorry. Thank you.
So
Thank you.
this is actually I wrote wrong. It is u cross v actually.
Because we cost X. Sorry, sorry. That is the confusion.
Right. So uh, now y is element of y and y is a topological space. So there is a basis element of y. So there exists by in basis of uh, so actually I should write basis of topology on x and basis for topology on y. So that y belongs to vy. Right. So since we know every basis element is open in the topology, that means it is elements of the topology. Clearly bx belongs to tau x and by belongs to tau y, right? So therefore we will get xy belongs to bx cross by, where bx is in tau x and by is in tau y. So this proves the first property, that every xy in the set x cross y, I can always find a open set in x cross open set in y, so that xy belongs to u cross v. What about the second property? So for second property, what we need to show, we have to show xy belongs to two basis elements. So the basis elements are of the form u cross v. So that means xy belongs to u1 cross v1 and xy belongs to u2 cross v2. Then we need to show that in the second property that there exists. So here what are u1 u2? Their elements open set in x, and v1 v2 are open set in Y. So there exists U3 cross V3 such that XY is in U3 cross V3 where U3 is open in X and V3 is open set in Y. Right, so this thing we need to show. So how we will show this? So this type of sets, if we try to see, so if I have two kind of intervals in R2, so this is for example U, this is V. So what will be U cross V? That will be kind of a rectangle, right? So let us say this is U1 cross V1. Same way, if I have another two, U1 is a subset of X axis, V1 is subset of Y axis, then I will get another rectangle which is U2 cross V2. Now can I find a rectangle? So these both rectangles contain some point, let us say X comma Y. So can I find a rectangle which contains
Yes, yes,
which
sure.
is contained in the intersection? So this we have observed when we discussed the in R2 the basis generated by the rectangular regions. Right. So there is a rectangle, but now I want to express that rectangle in terms of U2 V2 U1 V1. So what I can say here is I can always get such a rectangle. Uh, so what we know is U1 and U2 are open set in tau of X. So what is the smallest, what is the open set which is contained in U1 and U2 using the property of topology? So I'm repeating the question. If I have two open sets, then can I get a open subset of both of these sets which is contained in both of these sets?
Intersection.
Intersection, right? So
Yes, sir.
that is what I was asking. So since U1 and U2 belongs to tau x, U1 intersection U2 belongs to tau x. Similarly, V1, so this is U2, just don't confuse with U and V. So now I'm taking V1, V2 in tau y. Then, so now we are using properties of topology that if I have two open sets, then the intersection is also open set. Right. So finally, what we will get is therefore xy is in. So now I have two open sets in x and y. So I can construct open set in the x cross y by taking the cross product. So this element will belongs to B, the family B, because in family B what we have is one will take open set in x, open set in y, and we'll take the cross product. So this is open set in x, this is open set in y, so therefore this belongs to B. And not only that, so suppose I call this element V3. Then V3 is contained in U1 cross V1 intersection U2 cross V2. So is it clear that this is subset of this set? I'm saying this set is a subset of this set. Is it clear? Yes, Heman.
Yes, sir.
Is it clear?
Yes, sir. We can verify.
Yeah. So this is true, right? Because uh, U1 intersection U2 is subset of U1, and V1 intersection V2 is subset of V1. So therefore, this set is subset of this set. Same way, this set is subset of this set. So therefore, it is in the intersection. It is subset of the intersection. So the second property also holds here for this basis. So we verified that this set is basis on x cross y. So since now it is a basis, we take all the unions of these sets. So that is a topology. So let us just write down. So this proves this proposition and remark. So what is the the product topology? The product topology on x cross y is, so now once we have a basis, we can write it as a union of the basis elements. So union alpha u alpha cross v alpha, right? U alpha product v alpha, where u alpha is element of tau x, v alpha is element of tau y. So this is exactly the, if we want to use notation t topology on x cross y, this is exactly the topology, product topology. So what we have done is we have taken the open set and then we have discussed the what we have discussed is the topology. It is generated by those open sets. So taking the cross product of open sets. The same way we can construct uh, a basis also. So instead of taking cross product of the open set, for example, if I take the cross product of only basis elements, so let us try to see this. So theorem, so if B is a basis for the topology on X, and we take another basis, C is a basis for the topology on Y, then then can I get a basis on x cross y? So let us say D is B cross C, so that B belongs to B, C belongs to C. So is this is a basis? This is a basis for the topology on x cross y. So this is actually a statement, not a question. So so what we are asking here, can anyone, so is this statement clear?
Yes, sir, it's clear.
So clear, then tell me whether I am asking any question related to product topology. Is this question related to product topology?
Yes, sir.
Why?
Because sir सेम वहीं पे हमने ऐसे मतलब जो
That
टोपोलॉजी
is
ऑफ
same
प्रोडक्ट
x cross y.
लेके उसको
But I have not used product topology anywhere in the question. I am just asking that this is a basis. That's it. I'm not saying this basis is a basis for the product topology. If I say that, then I have to prove that. Right? So I think the question is clear now. So what is the question? Question is that we have to show D is a basis and every basis is on a some set. So that set is x cross y. So that is the only thing we are claiming here. So basically we need to check the both the properties of the basis. And proof is more or less same to the last proposition which we have proved. So again let for the first property, because again we will showing be it is a basis. So you take any element in x cross y, since x is in x, there exists b in the basis of the topology on x, so that x belongs to b, because we are given b is a basis on x, so that we are using. The same way, y is element of on x, so there exists element in the basis on y. So this is wrong. Y is the element of y, so that y belongs to c, right? And then we know that xy belongs to b cross c, because x belongs to b, y belongs to c. So xy belongs to b cross c, and then we know b cross c belongs to d. So first property of the that d is a basis is verified. The same way we take xy belongs to two such elements. So b1 sorry cross c1 and b2 cross c2, where b2 belongs to the basis b and c1 c2 are elements of the basis c. Then we need to prove that there exists b3 cross c3, so that xy belongs to B3 cross C3 which is contained in this intersection. Right, where B3 is in B, C3 is in C. Right, so again we will take the intersection as in the last case. So since so now what we have is xy belongs to these two sets, so that means x belongs to b1 as well as b2. So x belongs to b1 as well as b2, and we know b is a basis, so therefore there exists b3 in b, so that x belongs to b3 which is contained in b1 intersection b2. So we are using second property of the basis b. Similarly, y is element of c1 intersection c2. So there exists c3 in family c, so that x is in c3 which is contained in c1 intersection c2. Sorry, y is in c3 which is in the c1 intersection c2. Okay, so now we have two elements c3 and b3. So what we will do, since we are in x cross y, we will take the product, cross product. So xy, x is in b3, y is in c3, so xy is in b3 cross c3, and that we can easily verify that this is contained in b1 cross c1 intersection b2 cross c2. So just check this thing, you will require some elementary set theory to prove this, right? That if p3 is subset of intersection, c3 is subset of the intersection, then b3 cross c3 is subset of this intersection this. Right, so just try to prove this. It is just second right exercise. You can also prove this using Venn diagram, because we are in set theory. The properties of set theory can be proved easily using Venn diagram. Right, so this is the basis now, and then so now we have two bases. One basis on x cross y is this one. This is the basis on x cross y, and now I have another basis on x cross y. So one basis, the earlier basis, we have seen that it generates a topology which we are, by definition, we are calling it as a product topology. The topology generated by this basis we are not calling anything. We can denote it by just tau d simply. So question is that is product topology on x cross y is equal to the topology generated by this basis. So any idea how we will check this?
So we will show that this set contain each other, then they will equal. Okay.
Yes, so if we have two sets, we can check that. But now we have two topologies, which are the sets which has bases. So if you remember, we have discussed one result that one topology generated. We have discussed one result that I have two bases on X and two topologies. So B and B dash are bases on X. Then tau B contains tau B dash if and only if for every X in X and B in B there exist B dash in B dash, so that is it true or other way around? So you can use this result here. So do you remember this result? If I have two bases on a set, then I can compare two topologies, which one is weaker than the other topology and which topology is stronger than other topology. So we have compared the lower limit topology and the standard topology on R using this theorem,
Yes, sir.
right? So the same thing we can use here. So you need to find every basis of this form. You can always find a basis of this form for every xy, alright? And on the other way around, for every element of this form, you can always get a basis elements of this form. So that is exactly you need to check here. Okay, so I think this should be enough for today lecture. So any question regarding today lecture?